Alright, the energy of orbiting bodies. This is from topic 9 of the IB, and one of the things that you have to do is for the energy of things that are orbiting around planets is you have to derive their kinetic energy, their potential energy, and their total energy. This is going to be exciting. Buckle up. The potential energy. First thing you have to understand is that potential energy, hold on. Potential energy, let me get the paintbrush on. Potential energy, this is kind of strange. In actuality, the highest the potential energy of an orbiting body can be is 0. And most everything has a negative potential energy. It's almost as like you've got our sun here, and it's in a very deep potential energy well. And anything far, far away from our sun can have 0. But anything near our sun has a negative potential energy. And so even the Earth, which might be somewhere around here, has its own potential energy well. And when things orbit around the Earth, they've got a negative energy. And as they get infinitely far away, then you can have 0. That's sort of its own other discussion. And we're going to have to move on to the potential energy and how you calculate it, because this is potential energy. So, boom, there it is. The gravitational potential energy here is how much energy it takes. Let's say you've got your, let's say you've got your sun here, and if you have something that is infinitely far away, it has 0 gravitational potential energy. But then if you take this thing and you move it in to a distance r, it takes a certain amount of work to make that, to move that in. And costume change, woo! So if you need to derive the potential energy of an object that, let's say, is in orbit around a planet, one way that you can do it is using calculus. Now, here's that. And boom, there's the calculus way, but that's only if you care. You probably don't. The way that you could derive it using what the IB gives you is to look in the data booklet and look up their equation for gravitational potential energy, which delta V is the change in gravitational potential, and that's equal to the change in gravitational potential energy, which is different, divided by the mass of the object that's in orbit. You look up this delta V equation, and that's going to be negative G, mass of the planet, divided by the change in distance from the planet, times the same stuff on the right side. And then if you rearrange this, and let's just change this to an absolute value for gravitational potential energy, we get this equation here, which is our final derived value for gravitational potential energy, and it's the same as this one over here. So if we accept that potential energy is equal to a negative value, and now let's worry about kinetic energy. You should know that kinetic energy is 1/2 mv squared. And if you've got an object orbiting around, that's in circular motion. So you should know that F equals ma, that the force of gravity on something orbiting is this equation, and that's going to be v squared over r. You can cancel one of these r's, and our v squared turns in to capital G, capital M. These little m's go away over r. And now we substitute that in, And our kinetic energy becomes something clever, like this, which may not be familiar, but then if you rearrange that and you write it in this way, this is a much more useful equation. Now the IB data booklet does not give you this. They do not give you this. It kind of makes me sad, but they don't do it. But if you can get both these, deriving the total energy is a cakewalk. Total energy, you know, for something that's orbiting around a planet should be the sum of its potential energy plus its kinetic energy. That's easy. Now, we know its potential energy, wow, comes from there, but it's a negative. Crazy, eh? Over our kinetic energy, bow, just comes from there. And you end up with this crazy thing. And now you have to add fractions, which no one likes to do, but you just have to find a common denominator. How about 2r? What a great denominator. You end up with minus 2gmm plus gmm. I had to do some finagling to get that common denominator there. And then finally, I'm going to end up with a negative gmm over 2r is my total. And there you have it. We've got our potential energy up here, our kinetic energy here, and our total energy, which the key is total energy for anything in orbit is always negative. If it can escape orbit, then it goes to 0. Potential energy is always negative because it's close to the planet. Kinetic energy cannot ever be negative. It always has to be positive. And that's it. Woo!